Thank you for clicking on this video. This is problem 4. And in this problem, we have two objects. We have a ball that is thrown from the ground. This is ground, y0. And it is thrown with initial velocity of magnitude v naught up. At the same time moment 0, a rocket, this is a rocket was released. What does it mean that it is released? It means that at time moment 0, its velocity was 0. It was released from rest from a height h, vertically down, with an acceleration ay minus beta t. This is projection of acceleration, so acceleration is down. And this acceleration includes effects of gravity. So we don't need to worry about gravity for the rocket. They give us acceleration that includes it. Question: what constant beta should be for the rocket and the ball to land at the same time? What do we do? Let's start from the end. What does it mean that the rocket and the ball land at the same time? It means that the position of the ball at the specific time, let's call it t star. T star when they land, t star. The position of the ball at t star is 0. And the position of the rocket at the same moment t star is also 0. So we have the system of two equations. And all we need to do, we need to find the position of the ball at any time moment, the position of the rocket at any time moment, and then put them equal at that specific time moment and solve this system of equations for beta, for this constant. Sounds like a plan. Let's do it. Y ball at any time moment, position of the ball at any time moment. Let's think which formula we will use. I put some summary here. So the ball is moving up. Acceleration of gravity is down. And acceleration of gravity is constant. You can use these formulas, the definitions, but I will use for the ball, I will use our formulas, our shortcut for the case of constant acceleration. We can do it. Let's write y ball at any time moment. What is it? Ay for the ball will be negative g. My y is up, g is down, so it is negative g. This is ay. I keep going, any time moment, t squared over 2, plus v naught yt, v naught y, the projection of the initial velocity for the ball on y is positive. I put plus v naught times t, and the initial position for the ball is 0. It was thrown up from the ground. This is position of the ball at any time moment, and we are ready for the rocket. Now, what to do with the rocket? We know the acceleration of the rocket. Can I use this shortcut to write the position of the rocket? No, I cannot do that because I see time here. The acceleration is not constant. We derive these simple formulas when we took into account that acceleration was constant. That's how we integrated, and this is the result of the integration. Now we have to use these formulas. So I cannot find the position immediately. I know the acceleration. I need to integrate acceleration to find the velocity. What is y component of velocity for the rocket as a function of time? It is integral ay of t dt. What is ay? It is minus beta t dt. This integral, we take this integral, it is minus beta t squared over 2 plus constant that we will find from the initial conditions. Plus constant. Now let's find this constant from the initial conditions. What was v velocity for the rocket at time moment 0? That's what they give us at time moment 0. At time moment 0, this guy is 0, t is 0, plus constant is still here. And at the same time, we know that the velocity of the rocket at time moment 0 is 0. So the constant is 0. What is the final answer for velocity for the rocket at any time moment? It is minus beta t squared over 2. The projection of velocity with our choice of coordinate system is negative. Now we are ready to find position of the rocket. Position of the rocket at any time moment. We need to integrate Vy of t dt. What is Vy for the rocket? It is minus beta t squared over 2 dt. I take this integral. Let's do it together. It is minus beta. Then it is t cubed over 3 and times 2. So it is minus beta t cubed over 6. And we don't forget to generate new constant. This constant is different from this one. We need to find it. And as always, we find it from the initial conditions. What was the position of the rocket at time moment 0? That's what they give us. At time moment 0, the rocket was at height h. Okay, we use it. Time moment 0, this guy is 0 plus constant, and this is h. Position of the rocket at any time moment is equal to minus beta t cubed over 6 plus h. Now we know both formulas. We know the position of the ball at any time moment. We know the position of the rocket at any time moment. We are ready to bring this information into our equations, our system of equations, and find the position of the ball at that specific time moment, the position of the rocket at that specific time moment, and put them equal to 0 and solve for t star. I will erase. Stay with me. Now we are ready to write these two equations. I write y of the ball at t star minus g, this equation, t star squared over 2 plus v naught t star. And this is equal to 0. And the second equation for the rocket, minus beta t star cubed over 6 plus h is equal to 0. This is my system of equations. Two equations, two unknown variables. I don't know t star and I don't know beta. We can solve this system of equations. I will use the equation 1 first, and I will solve equation 1 for t star. Let's factor out t star. Then what do we have in parentheses? We have minus g over 2 t star plus v naught, and this is equal to 0. It has two roots. One root is t star 0. We are not interested because that's when the rocket and the ball started their motion. We are interested in the second root, minus g over 2 t star plus v naught is equal to 0. What is t star? T star is equal to 2v naught over g. Okay, now I will take this t star and I will bring it into my second equation that I need to solve for beta. Minus beta over 6, right here, t star cubed will be 2v naught over g cubed plus h. And this is equal to 0. Well, it's one equation, one unknown variable, beta. We can do it. What is beta? Beta is h on another side of the equation. 6 on another side of the equation comes here. G cubed. And I divide it by 2v naught cubed. 2 cubed is 8. And then v naught cubed. We simplify it a little bit, and I get 3 over 4 h g cubed over v naught cubed. Now let's check the dimension. I cannot check this 3 over 4, but I can check the dimension. Beta has to be in meters per second cubed, because acceleration is in meters per second squared, so meters per second cubed times second, it should be correct. It has to be correct. Meters per second cubed. Let's check what I have here. H, what is H? H is in meters, right here. G is in meters. G is meters per second squared, so it is meters cubed now. And then seconds cubed, seconds squared and cubed is seconds to the 6, meters per second squared cubed, and now V naught cubed, meters cubed per second cubed. Okay, what's happening? Meters cubed, 6 minus 3 is 3, and I get meters per second cubed, as it has to be. The dimension is correct, and we found our beta. So we found beta such that the rocket and the ball land together. Instead of putting each of their positions equal to 0, one of these equations could be just put one equal to another, and you will get the same result for beta.